Hello everyone, and welcome to this live talk on applied AI for wireless and radar applications with MATLAB. My name is Abderrahim Belissaoui, and I'm part of the CS technical team. My background is in signal processing, radar, wireless communication, and AI. And today I would like to walk you through the MATLAB AI workflow for different applications, but specifically for radar and wireless. Our agenda for today going to start with an introduction where I'm going to share some challenges that can be solved with AI, in challenges in wireless and radar. And also we'll shed some light on different applications that we have capabilities for when it comes to AI. Later on, I'll dig deeper and speak about the AI workflow with MATLAB. Then we break it down, we speak about the applications or the application of AI in wireless communication on radar. And then I have a summary for you and a call to action where I'd like to connect with us to see how we can support you moving forward. All right. Let's start with speaking a bit about the different applications of AI across different domains and areas using MATLAB. And because we have a varied interest in the room, I want to highlight how MATLAB AI capabilities span a wide spectrum of application and industries. We see use cases in traditional engineering domains like radar waveform classification, LiDAR for 3D object detection, and in wireless communication for applications like channel estimation. At the same time, applications such as predictive maintenance, robotics, path planning, and the control systems show how AI can optimize industrial operation and automation. On the data-centric side, geospatial analysis with hyperspectral image classification and computational finance for trading and risk management illustrate how AI can support the decision-making in complex environments. In these high impacts and in high impacts areas like automated driving and medical imaging and audio processing, we see how deep learning enables real-time perception, detection, and interpretation. These reference examples that I'm including in this slide aren't just demonstration. They show how MATLAB AI tools are being applied to solve real problems across different industries, domains, and workflows. So whether your work is in hardware or software or analytics, or you are doing some research around these areas, there is likely a relevant use case here that speaks to your challenges and opportunities. So in today's talk, we're going to focus more on radar and wireless communication. But before that, let's talk about how AI can help when it comes to RF systems. And RF system here, we mean radar, wireless, or electronic warfare. As radar, wireless, and RF system grow in complexity, traditional design approaches struggle to keep up with rising performance demands. AI offers a powerful alternative enabling more flexible system architecture, improved performance, and better overall results in this increasingly challenging environment. AI is driving innovation in radar and wireless communication systems, especially as we move toward more advanced 5G, 6G, and cognitive radar architectures. Applications span target classification using RCS or micro-deploy information, target classification based on RF fingerprints, or classification of receivers for waveforms from radar and wireless communication. AI also enables anomaly detection, object identification in SAR images, and accurate channel estimation, making system more adaptive, intelligent, and responsive to dynamic or to the changing environments. And there are more other applications that I will share in the next slides. This slide outlines the taxonomy of AI, machine learning, and deep learning, distinguishing between supervised learning and unsupervised learning. In radar and wireless application, classification tasks like modulation, identification, and localization rely on labeled data, while regression is used for tasks such as beamforming, weight measurement, or estimation. Also, regression is used for tasks such as digital predistortion, component design. And that's mainly for the compensation of nonlinearities caused by the power amplifier. Deep learning extends these methods to handle more complex patterns and data structures. AI works with different data types, and the same applies for applications like radar and wireless applications. We typically think of signals that end up as complex baseband. This is quite common in radar and wireless application. We usually end up with complex baseband signals. These signals can be used as input to AI networks. But images can also be generated. We can also transform these signals into what we call heat maps or spectrograms or scalograms. For example, microdoppler information or microdoppler signature, time frequency maps, and array patterns are examples of images that are generated from data related to RF systems like radar and wireless or EW systems. Let's begin with a quick introduction to the AI workflow to set the stage for what we are exploring today, which is mainly AI applied to wireless and radar applications. AI, or artificial intelligence, is the broad idea of machines mimicking a human intelligence. Within AI, we have machine learning, which plays a central role, which is all about enabling systems to learn from data rather than relying on hard-coded rules. Machine learning, in this case, or machine learning comes in different forms. First, the supervised learning, which uses labeled data to make predictions. Then we have the unsupervised learning, which enables finding patterns in data without labels. And then another approach or another type of machine learning is the reinforcement learning, which learns through interactions, something like trial and error or rewards. And then there is deep learning, which uses neural networks with many layers to handle complex tasks like image recognition and speech processing. Together, these approaches form the foundation of many intelligent systems that we use today, like the recommendation system that they use to recommend the products or something. So when deciding between choosing between classical machine learning or deep learning, data type is a key factor. Machine learning works well with structured tabular data, while deep learning excels with more complex data like data type, like time series, images, and videos. Matching the approach to your data helps ensure better performance and deployment efficiency. For our application, or for today's application that we would like to elaborate on in details rather than wireless, we get time series or signals. Let's get into the specifics of what I'm talking about. When I talk about an AI workflow, a simplified view results in 4 main stages. The first stage is data preparation, AI modeling or algorithm and AI modeling, simulation and testing, and then deployment. It's also important to note that this workflow isn't linear. It's not linear, but in many cases, it's iterative, especially when testing, that modeling covers improvement that need to be made. To provide some more context of how this workflow could be used, Let me walk you through the workflow step by step. Talking about data preparation, we usually need first to gather some data or generate some synthetic one. Data preparation is beyond just data manipulation. Data labeling is required for any kind of supervised learning algorithm, and this can be time-consuming and error-prone. For deep learning models, MATLAB provides data labeling apps like the Signal Labeler app that enables you to label signal, talking about this app, which enables you to label signals for analysis or for the use of machine learning and deep learning application. We have other labeling apps too, and all of which can generate code for use. For example, you have audio labeler if you are doing some audio processing or speech recognition, image labeling, image labeler if you are working with images, LiDAR labeling if you are working with LiDAR data, and so on and so forth. Data preparation is a critical step and often the hardest. Today, data is noisy, coming from different sensors in different ways. Before modeling, it must be cleaned, organized, and in many cases transformed across time and frequency, and then or time frequency domain. MATLAB tools like Diagnostic Feature and Designer helps with automatically extracting features, enabling faster and more accurate feature engineering. Let's move on to the second step, which is the AI modeling. The second step in our workflow, the AI modeling, as I said. The one that perhaps gets the most attention is this step called AI modeling. Within the MATLAB environment, you have direct access to common algorithms used for classification and prediction, from regression to deep learning or to deep learning networks to clustering. And with MATLAB, you can easily use pre-built models and perform some transfer learning or just use them as they are. We also have reference examples to help you get started and build on the top of them. And these reference examples are available for different applications that I mentioned in the very beginning. I mentioned apps for data preparation. We also provide apps for building, testing, and fine-tuning machine learning and deep learning models from scratch. For deep learning, MATLAB pre-built apps like Deep Network Designer app helps you build, visualize, and edit deep learning networks. A bit more about this app. With this app, you can access pre-trained models. You can visualize and import an imported model. You can create a model from scratch. You can analyze a model, import and train models, and then you can also export your AI modeling as a MATLAB code. There is also an app to manage experiments. I'm talking about the experiments manager here, which allows you to explore hyperparameters, monitor training progress, define experiments with MATLAB code, keep track of your work, and most importantly, export model results. For classical or traditional machine learning applications, supervised one mainly, there are learning apps to try different algorithms and find the best fit for your data sets. This is a video showing the workflow of Experiment Manager. As I described this, or as I highlighted this, you can create baseline, or you can create a bench of experiments and train them on the same data set with the different combination of parameters. Also, you can track the progress, stop experiments, and so on and so forth. In this case, you will need to write a few lines of code to specify training options, data augmentation, data preparation, data pre-processing steps that you would like to loop over. If you have done some progress using external or third-party frameworks like PyTorch or TensorFlow, MATLAB allows you to import and integrate these models alongside with your MATLAB code or MATLAB applications. You can, for example, import TensorFlow models using the TensorFlow importer by just like installing a support package that will allow a seamless integration. You can also import from PyTorch via ONNX, and also if you have your model in another framework which is not PyTorch, not TensorFlow, you can always like import it to MATLAB and perform some transfer learning using your data sets. This workflow is bidirectional, so you can export also from MATLAB to these frameworks. Deep learning training can take a long time, and this is very common and everybody knows about it. With our cloud support and third-party integration, you can mold the training to the appropriate compute platforms such as GPU devices, or if you have access to public cloud or private cloud and so forth. The point here is that a single model in MATLAB can be moved seamlessly to the appropriate compute platform, saving huge amounts of time and use that time for the development. To summarize the modeling steps within MATLAB environment, you can have access to all the algorithms and models that are available out there in the community. Building on that, you can customize those models, or you can also work with them at the code level through apps or through apps. So you can also write code. I haven't mentioned so far that if you like to write code, you have the option to build AI models based on code, same in other programming languages. But we recommend to use these apps and low-code features available in MATLAB. And also, MATLAB can accelerate training to the appropriate by upscaling to the appropriate compute platform, and can engage with the AI, and also can engage with the AI community by importing and exporting to frameworks like TensorFlow and PyTorch. Let's move now to the next step, or to the third step, simulation and tests. Once you have your model ready, you can integrate it into its bigger system and verify and validate the bigger design. This can all be accomplished with an overall system simulation that handles not just the algorithm or the AI algorithm, but also simulates the behavior of the model within its bigger system. And that's, of course, in Simulink. If you want to know more about integration of AI into model-based design using Simulink, we can have a separate session for that. So yeah, please let me know in the chat if you would like to have a session about the integration of AI into model-based design. The last step in the simplified AI workflow is the deployment, taking your model from the environment, MATLAB and Simulink environments, and then deploy it to embedded hardware. MATLAB and Simulink offer a unique code generation and application deployment frameworks that allow models developed in MATLAB or Simulink to be deployed anywhere. When I say anywhere, I mean hardware or software. Can generate a production code that can be C, C++, or HDL or CUDA code and deploy them to the right hardware. Or if you would like to deploy your AI model into an enterprise systems, you can use the different compilers that will result in an executable that you can install on your machine or your team machine that they don't have access to MATLAB. You can also generate a Docker container and DLL libraries, Java application, and so on and so forth. You can also generate a Python package if you would like to. Automatic code generation and deployments in this case eliminate coding errors. So instead of using MATLAB and Simulink for simulation and testing analysis only, you can use it for the entire workflow. That will eliminate coding errors, as I said, and that's a value driver for any organization adopting this code generation and application deployment framework. Sometimes we need to compress our models before deploying them, and that's where the model compression comes in handy. This compression can bridge the gap between AI modeling and embedded deployment. Reducing the size of your model is actually very important, as sometimes your model might perform pretty well in the environment in MATLAB, but when you deploy it to hardware, it might not work as expected, and that's because of its size, not because of the tools. So the solution in this case, compress it using any of these techniques or a combination of them, like pruning, quantization, and so on and so forth. You can also iterate over design and then understand how you can reduce the size. There are other compression techniques like knowledge distillation, and then low rank factorization, and so on and so forth. I didn't mention them here, but I'll be glad to connect later on and speak about this compression in details. So the AI workflow for building deployable AI models now has 5 steps: data preparation, AI modeling, simulation and test, compression, and eventually deployment. Please note that this model or this approach is iterative, and it helps you move from a model that is accurate to a model that can be deployed efficiently. Okay. Let's now speak about how AI can help with improving or making this wireless communication system secure and sophisticated. And for that, I would like to bring back the AI workflow with MATLAB, which we explored together. And this time, I would like to highlight some tools that you can use for AI when it comes to wireless applications. For example, you can use this wireless waveform generator to build a data set of different modulation schemes or different wireless signals. Moving forward, you can use a pre-trained model, or you can train your custom model using the different apps that I spoke about before. Then for simulation and test, you can integrate your model into a Simulink design of a wireless communication, or you can test a prototype with an SDR or a radio platform like this Adam plot. Then the deployment in this case can be into an FPGA, and for that reason you can use an FPGA-based radio and deploy your models, your AI wireless model into a radio that is based on an FPGA. In this case, you're going to need to generate an HDL code. Applications of AI for radar and wireless include, but not limited to, spectrum sensing, channel estimation, digital predistortion, and array pattern synthesis. And of course, there are more applications, as I said, which you can explore by following this link. Let's explore some of these applications in more detail and how AI is being applied in areas like spectrum sensing, channel estimation. We start with spectrum sensing, which is actually which is all about detecting and identifying what signals are present in a given frequency band. This task, or this spectrum sensing, is critical for tasks like dynamic spectrum access, interference detection, and cognitive radio architecture. So we would like to design a system that monitors a wide band of spectrum, label 5G, LTE, and maybe radar signals in time frequency domain. We are here talking about the spectrogram, which is nothing but the plot or the visualization of the magnitude of the short time Fourier transform. Sorry. So for that, the workflow is the same. We first start by data preparation. In this case, we are generating 5G and LTE signals using the wireless waveform generator app. Then we calculate the spectrogram. We convert these signals or these one-dimensional signals to image like plot, or let's call them spectrograms or heat maps. Then we label the pixels of the spectrogram as 5G, LTE, or noise. And then the second, or the step 2 in the workflow is to train and optimize the network. And you have different ways. You can design or reuse an existing deep neural network, and here you can do the transfer learning, or you can just like use it as it is. You can also import deep lab, or let's say pre-trained models for semantic segmentation, because here we are dealing with a segmentation problem. And then you apply transfer learning using your data sets. You can optimize the hyper parameters as well, using the experiment manager to find the optimal set of parameters for your training. Then when it comes to testing your model, you can do it with synthetic wireless signals, or you can capture some over-the-air signals, which will come from an SDR platform, and then test the correctness or the performance of your model on that real-world signals. To enhance the training data, you can always you can keep acquiring and augmenting, labeling your signals, and then repeat. And remember that this workflow is iterative, as I said before. So you can always go back to the first step or the first phase, and then try to improve your model. Another use case or application is channel estimation. And channel estimation, for those who are not familiar with this, is the process of finding out a model or figuring out a model that represents the communication medium, so we can understand how it affects transmitted signals. The main goal of a channel estimator is to accurately recover the original data at the receiver side. There are some traditional algorithms that we use often. I mean, we use them to model this channel, but AI proved to give better performance. And the same thing we said about spectrum sensing can be said about channel estimation, same workflow. I mean to say, we start with data preparation. We use the waveform, the wireless waveform generator, to generate some 5G standard compliant waveform. When I say compliant, they comply with the standards of 3GPP. And these waveforms will not be very sensitive, but it will reflect the impairments that we have in the channel. Alongside with that, you can include this pilot signal to make your data more realistic. The next step is to design the AI model or the algorithm, the AI algorithm. And that includes deep learning, design and training, simulate the 5G transmission, visualization and performance comparison. So we are including testing here. Natural step or natural next step is to deploy your AI model or your channel estimation model, which is based on AI, to an FPGA by generating an HDL code. Before we move to the AI in radar or AI for radar, I would like to showcase a quick demonstration about the spectrum sensing. Just go back here. Let me jump to MATLAB. And then let me just like tell you a bit about this demonstration. So as I explained, spectrum sensing is all about figuring out the spectrum content in a specific frequency band. That was achieved, or that's usually can be done using some traditional classical algorithms. But deep learning found a way to spectrum sensing as well, and it helps with identifying 5G, LTE, WLAN, Bluetooth, and so on and so on. So all this can be identified, and that's going to help us with understanding the spectrum content. The purpose of that, as I explained it, is to understand your spectrum. Has the main users, maybe if you have some users that are should be prioritized. Also, you have some users that are not, primary, and they can wait. So in this case, you need to understand your spectrum to make it, or to take control over it. So this example shows how to train a semantic segmentation network using deep learning for spectrum monitoring. So we are doing spectrum sensing for spectrum monitoring in this case. One of the use cases of spectrum monitoring is to characterize spectrum occupancy. I mean here, knowing the different signals that are available in that spectrum. The neural network in this example is trained to identify 5G new radio, LTE, and WLAN signals in a wideband spectrum. Are you going to be able to figure out that here we are talking about the same workflow I showed in the slides? First, we generate data, we prepare it, and then we design a model, or we use a pre-built model, and then we test the model, and then you can deploy it. So deployment is not covered in this demo, but we will be more than happy to showcase how the deployment of AI models work. Let me jump to the section related to generating data. Or maybe we can talk a bit about the workflow associated with this. So we are talking about data that was captured using an SDR. And this data includes WLAN signals, 5G signals, LTE signals, some noise, and some unknown signals. The workflow is simple. As you can see, we capture and label the training data. We train the network and label the bandwidth. We use trained network, and then we identify edge cases. So, and again, it's an iterative workflow. I mentioned many times that you can generate training data interactively using the wireless waveform generator app. But you can also use that app and then export to MATLAB or generate a code from. And that will help you with reusing that code and then iterating over different functions that are here, or that's going to be used to generate the different waveforms. I mean here, 5G, NR, the LTE, the WLAN signal, the noise, and so on and so forth. So the 5G new radio signals were generated using this configuration, mainly the bandwidth and the subcarrier spacing. The LTE has different variables, the reference channel, the bandwidth, and the duplex mode for the OFDM. And then there is a different configuration for the WLAN signals. We are talking here about the bandwidth and the MCS. So in these examples, I'm using some helper functions that help me with, for example, generating the dataset instead of wasting, time to write the code. So I put them in some helper functions, and they serve different purposes. We're going to explore that in a moment. If you don't wish to generate the data again, so just set this training data source to use downloaded data, okay? And then you can also use captured data from the SDR platform. And once you run this section, if your data is not available, you will need to wait a bit so it gets the data in your current folder. For me, in my case, I already downloaded the training data, and I believe I'm ready to just run this section and see what we're gonna get. So I didn't run this because some of this didn't run because my data is already there. Okay. if you are asking the question where I can find these functions, they are shipped with the example itself. So this example is part of the, I believe, communication toolbox, 5G toolbox, LTE, and so on and so forth, because we are here using functionalities from different toolboxes. And next step is the AI modeling, if you remember the workflow. And for that, we would like to choose a deep learning network. The base network, or this is the network that we would like to use, can be custom. In this case, you're going to do the training from scratch. You can build this from scratch, or you can use a pre-built model like ResNet 18 or ResNet 50. Okay. Then this is the function that download the data. And because it's already there, so MATLAB just keep this section. Later on, we can load the training data because we are trying to, we downloaded it, now it's time to load it into MATLAB workspace so that we can start using it. We set this use captured data because we wish to use the real world data coming from the SDR platform. And then we are using image data stores, which are, these image data stores are very useful, and they enable you to efficiently load a large collection of images from a disk. And then what we're gonna do, we're gonna just convert them to spectrograms. Just run this. So my data is now in the MATLAB workspace. If I click on this, I'll be able to see in the workspace it's here. Next is to analyze this data, understand the frequency of occur of different signals, 5G signal, the WLAN signal, the LTE signal, and so on and so forth. And for that, I'm plotting the frequency or the heat map of the of this data. So the reason I'm doing that, I would like to check how diverse is my data and how rich it is. So if my data is all 5G NR and there's nothing related to, let's say, LTE, I'll not be able to get a good model. So that's why this data preparation step is time consuming, but it's very, very critical for AI modeling. So what you see here is the frequency of happening of different signals in our training data. We have the new radio, the LTE, WLAN, a lot of noise, and some unknown signals. So let's try to now manipulate this data, split it into training data sets, validation data sets, and then we can also keep some samples for testing. By running this, I'm splitting my data into 3 categories or 3 groups: training data, validation data, and then test data. If I selected custom, I will need to design my model from scratch, but for the sake of time, and because we have some more content to cover, I'll just do transfer learning based on I will actually use a model that was trained before just to showcase how you can test that model and evaluate its performance. So this Deep Lab V3 Plus creates a semantic segmentation network model, and it requires a support package. I'd recommend that you try this after the session, and then you will find that it requires that specific support package. Next is to design a simple semantic segmentation. This will not happen as I'm not using a custom. Okay. Just go back here. I think I run this section. And for the phase or for the stage of building an AI network, we usually start with the training options, and that includes the optimizer. We are using here sigmoid function, the number or the mini batch size, the max number of epochs, the learning rate, and so on and so forth. So all of this should like be common to people doing AI. So these training options are required for training our AI model on our data sets. Let me run this section so that I get the training options ready for me to use. As I said, I'm not going to do the training here because we don't have enough time for that, but I would be happy to, connect again after this session maybe and try to do the training. I try to do it, and it sounds it takes a bit of time, and but that doesn't mean it will not work. It will work. Just try to switch between. Let me just show you in a moment. Just switch between use a trained network to your train network now, and that section gonna run, and you're gonna start the training of your AI model. Right, so let me just go straight to this. I think I run this section. Now that the model is available in the workspace, let me just show you this model. Open net, and this is what we get. It has layers, connections, and so on and so forth. The other way to visualize this is to use deep network designer app. As I said, it can be used for building models, AI models from scratch, but it can be also used to visualize networks, AI networks. So what I'm going to do now, just go into, so I'm just going to select this import from workspace. Let me go back here. So it seems like some of these small windows are going to the other side, and then I will select this net. Then OK, and the app gonna open the model. Might take a bit, but as you can see, this is our model. We can zoom on specific region to understand what the model and what it does exactly. So so this is the input layer, then the convolution layer, and so on and so forth. So basically, this is a CNN-based architecture or convolution neural network-based architecture. Just to this was just to show you this deep network designer. As I said, you can create your own model and train it within the app without going outside or without generating the code. But if you would like to export, you can export as a MATLAB code, or you can also export to Simulink. So now that our model is ready, we can go ahead and start testing it. So that's the testing and simulation stage, and we would like to use the recorded data from the SDR. What we would like to do now, we would like to evaluate the semantic segmentation model that we just, I would not say train it, but the model that we just imported from a pre-trained model already. So basically what I'm going to do here, I'm going to show the classification and the misclassification in a plot called confusion chart. And while waiting for that, so another way to test is to test with captured data. I believe this was with the generated data. Okay. So what it's doing now is testing with, let me just show that. So we are testing with the data sets for testing that we get from splitting our training data into training data sets, validation data sets, and then testing data sets. So let me just go straight to this. So you can also identify 5G, NR, and LTE signals. So as you can see, this testing can be done or can happen in at different levels. You can test using the confusion matrix, but you can also test with the data itself. Let me just go back. I believe we have got the confusion matrix with sensitive data, as you can see here. And as I would say that my model is performing quite well. Yeah, there are some misclassification. For example, this LTE was this LTE was classified as new radio and so on and so forth. So there are some misclassification, but this model can be improved heavily by looking at some maybe data preparation, normalization, or maybe data augmentation. But you can also use some other networks, or you can try to customize your network and perform the training, and you might get some better performance. But for me, this is not bad, as I'm dealing with signals that they look just the same. And then you can also test with captured data. And that's going to be the end of this section, or end of this demonstration. With the test data, my model is performing pretty well, better than with synthetic data. This data was captured using SDR. Again, just want to mention this so that you remember what I'm talking about. And another way to test is just to test with the dataset itself, because here we are doing some segmentation. We can test with the spectrogram. And this is the true or the labeled data, the ground truth. And this is what we got using our estimated channel, or using our deep neural network segmentation architecture. So we got this, and I believe it's performing pretty well. And for me, I would like just move forward and try to deploy this model if I'm working on a project about spectrum sensing. It performs pretty well. So yeah, and also you can see the normalized confusion matrix. And so the conclusion here that the new detection rate increases to more than 99% with the captured data. Another thing that you can do is to identify 5G, NR, and LTE signals in spectrogram. I'll not go to this, it might take a bit. And you can also connect your SDR to your machine that has MATLAB installed and perform what we call over-the-air classification of your, or over-the-air spectrum sensing or spectrum monitoring. Okay. Let me just switch back to the slides and speak about application of AI in radar. Okay. And before that, I just want to mention that I have included here a couple of examples that I'll highly recommend that you explore later on. So these applications spans, different use cases, from sensing, spectrum sensing, to channel estimation, to channel state information, feedback estimation and enhancements, and so on and so forth. So I highly recommend and invite you to explore them after this session. And if you have any questions, just please reach out to me or to my team, and we'll be more than happy to support. Because it's actually the same workflow like in wireless, we can apply the same AI MATLAB workflow, or MATLAB AI workflow, to radar application, from data collection and feature extraction to training and deployment. Here the hardware is different. We are talking about maybe some radar development kits, and then what we got some heat maps, range Doppler, range angle, and so on and so forth. And then we label that data. We build our model using the deep network designer, or programmatically using the code. Then we test using the confusion matrix, and then we can connect our radar development kits to MATLAB seamlessly and perform this realistic testing by target identification, so we can use that. And the deployments, you can also generate a C code from your AI model and then deploy it to the same development kit if you have enough processing resources. Application of AI for radar includes, but not limited to, radar cluster suppression, SAR, or synthetic aperture radar target classification, radar waveform classification, or you can use AI with radar for health monitoring by estimating the vital signs of human beings. And there are some more applications that you can explore from here. A use case that I would like to talk about in details is to remove clutter from the radar scenes or maritime radar scenes using neural networks. So here we are designing a scene, a radar scene that has two targets alongside with surface clutter, and this surface clutter are also modeled using the different variables like wind direction, wind speed, and so on and so forth. And what you get at the end, you're gonna get non-labeled data that includes or that contain clusters plus targets. But you can also do the labeling by removing this and keeping only where the targets are located. And by using a neural network, you can filter out the cluster as you can see here by removing the cluster or the C cluster, because we are talking about maritime radar, and then you end up with your targets, and some noise is still there or some cluster are still there, but can be, I mean, quickly and easily removed. Another use case is radar waveform classification. You can build and test a deep learning model that classify radar waveforms like rectangular or linear frequency modulation pattern and so on and so forth. You can classify them using just CNN networks, and that will help you recognize modulation types and the application of that, or the application of finding out which modulation type is that, is cognitive radar. And same we said about wireless, we can use some specific type of SDRs to validate our model. To get started with building AI applications, let's say AI-driven radar applications, you have tens of examples available under radar toolbooks and some other toolboxes. And that includes radar target classification. You can also use it for generating novel radar waveforms and so on and so forth. So you will have these slides. I will recommend that you check out all these examples. Before that, let me quickly show you one example of how to use AI in the radar context. Let's just go back to that use case. That use case is maritime radar cluster removal with neural network. I believe this is the one. So what I'm doing here, or what is this example about, is about removing the cluster, C cluster, or sea surface cluster from a maritime radar scenes. So you can generate this data using radar toolbox functionalities. You can build a radar that generates synthetic data sets of radar scenes or maritime radar scenes. And I have done that before, so I will not go to that. I will not show how to create data sets, but I will be happy to connect later on and see what we can do when it comes to generating synthetic data for your maritime or for other application or for the other types of radar. In this case, we are talking about double PI, or what we call plane position indicator. So let me just set the stage by generating or by setting the random seed generator to default. And so if you would like to download the data, you need to run this section. If your data is already loaded or is already there, so you can just load it. So the data is available here, as you can see. So sorry, it's here. So I don't need to generate it from scratch. Now let's explore this data set. So as I said, the input is the scene with the cluster and target, and the response is the targets only. We can perform the training. I'll just prepare the data set. I loaded it, and then I'm splitting it into training and response. This is the training, or the images for the training, and these are their responses. Later, I can start designing my neural network interactively using the Deep Network Designer. or programmatically by writing code similar to what I have here. Now that you have the model, which is actually nothing but a convolutional neural network architecture, I'm ready to start the training. And if you remember, for the spectrum sensing example, I showed that you first need to set the values of the training options. In this case, we are using a difference optimizer, which is Adam, instead of the sigma wave function. And the metric or the optimization metric is the RMS. This is a type of error that we look at, and so on and so forth. So all the training options that we saw before are actually quite similar here. Then because I selected do training, I believe I will be able to do the training. So my training just started. I'm using a helper function for that to track the progress. It will not take too long, so maybe 1 minute or something. That's a small model, as you can see. It's quite a small model, and our data set is also quite small. So this progress shows the training and validation loss, which will decrease until an error floor is hit. So I believe something around here. So if you'd like to improve these results, you can add more samples to improve the performance of this network. So once the model is there, we can start evaluating it by using this helper pro evaluate results, which will call the images from the testing dataset and apply the network and try to see how it's gonna end. And there you go. So you have now the loss plot, and it shows like it might perform pretty well. Let me just like run the evaluation phase and see what we're gonna get. As I said, I'm using this helper function, which is available in MATLAB. It helps you with calculating or like applying the network that you got on your test data. So this is what we got. As you can see, it's quite a good outcome or quite good performance. Yeah, we still have this clutter around the radar or around the ship that has the radar, the maritime radar, but this can be removed by a spatially aware layer that you need to add to your network. This model or this example can be customized further to, improve the results. Let me just go back to this slide. So as a summary, in this presentation or this live talk, we shed some light on how AI can integrate into radar and wireless application, walk with you through MATLAB AI capabilities and end-to-end workflow for building AI-based solution, covered practical radar, the maritime radar example, and then we demonstrated how AI can help with spectrum monitoring using that MATLAB example. A call to action can be or should be, or I invite you to try the examples that I showed, the examples that I attached to my slides, and also you can dive deeper into examples that are relevant to your AI application. If you are not doing wireless or radar, you can go back to the first slide where I showed all the application. Then you can also explore further learning by watching some videos and webinars that are available on Matok's documentation or Matok's website. And another way to learn and expand your knowledge of AI in MATLAB is the technical articles. So these are written by some experts, so I would recommend to check that as well. Or, and this is the optimal, call to action, is to connect to us with and share with us your follow-up questions, or maybe you can schedule a session at your convenient time with you and your team, of course. You can also reach out to us if you have any support cases that are related to MATLAB and Simulink and their add-ons, not only to this webinar, at support at simulations.com. If you would like to try these examples and you don't have a MATLAB or you don't have a MATLAB license, you can reach out and then we're gonna be happy to generate a trial license for you and support you with making use of it.